Hello physics students, this is the second video from the last assignment. This time I'm going to take the opportunity to show you a different way to look at the mass change due to a beta decay. So first let's go through it in the book's way, and then let's look at it with a more direct approach, in my opinion, because this is right after this, after you read the next page on neutrinos and so forth. And we may actually have an opportunity to go back and look at neutrinos in a little more depth at some point. I have a nice film on that if we have some time. But once you've looked at neutrinos, we're going to skip back to chapter 26 and pick apart E equals mc squared in a little more depth. And then we'll go and finish nuclear fusion and fission, and we'll be done. Okay, so I thought that this was a good opportunity to look at E equals mc squared kind of for the first time. So first let's do it the book's way though. So it says energy release. So we've got a carbon-14 isotope, and it looks like it's decaying with beta decay to become a nitrogen-14 isotope. And this nitrogen-14 isotope, because it decays by beta emission, it gains an electron, that nitrogen does, so that nitrogen is no longer neutral. So notice we'll be looking at E equals mc squared. The way the book does it, it doesn't really do it directly though. I don't know, I kind of don't like this. This is kind of more of a chemistry approach. So let's do it that way first, and then I'll show you another way to do the problem. So what we're supposed to do is figure out how much energy is released during this decay. So let's do our problem solving thing and say, okay, we're trying to figure out the energy. That's the key. So I think we're going to do that by basically seeing how much mass was lost. So this delta M equals mc squared, you can see the delta. Delta just means that the mass was changing. So of course during this decay, there's going to be some kind of change in mass. So let's see what that is. So it says the total mass in the final states. That means they must be looking at the daughter, the product, that nitrogen guy. So it's going to be that nitrogen guy, which has 6 electrons plus the 1 electron that's emitted as a beta particle. Okay, so that's why you have 7 there instead of 6. So it's like the nucleus of this guy, which is 7 protons and what is it, 7 neutrons if we go 14 minus 7, plus 6 electrons. So it's like undercharged basically. That's why it's got a positive charge. And then there's this outside beta particle, which is just 1 electron as well, indistinguishable from a normal electron, but it's kind of out there separate. Okay. All right, so this is equal to the mass of the neutral guy. I don't even think you really even need to think about this. This is just them saying, oh yeah, it is actually equal to this, equal to the neutral nitrogen nucleus, even though that's not what actually is happening. So, of course, 6 plus 1 is 7. So whatever, you don't even have to realize that. So they say from Appendix B, the mass of this product is going to be this guy. So the only reason they really did this is because otherwise you'd need to figure out the mass. Oh my gosh. You'd need to figure out the mass of that part up here, which just has 6 electrons, excuse me. And there's probably not something in the tables that gives you that mass number. So that's why they're saying, hey, just think of it as just a regular old neutral nitrogen nucleus and get the mass out of the table. So let's go to the table. So that guy I don't think is actually in the periodic table. So we're going to have to look for nitrogen. Looks like in the back of the book they have nitrogen 13, 14, and 15. There's probably other isotopes of nitrogen, but we wanted nitrogen 14, didn't we? So we're going to pull this number right here. Okay, so that's where they got this number, so out of the appendix, okay? Not off the periodic table. It doesn't have isotopes, it just has the most common element, the most common isotope. It didn't have that one. Anyway, so the mass difference is going to be, where's this number coming from? So we're going to subtract this guy, but where did this number come from? Let's go back and look at that table. Well, what are we doing here? Remember, we're going from carbon 14. I bet that's the carbon 14 parent. So let's go see. Carbon 14 is right here. 14 point, and it's got 3242. 3242. I see that. Okay, so this guy must be the carbon. So we're looking at the difference between the original carbon and this guy, which is an amalgamation of the daughter nitrogen, and also it kind of includes that beta particle. Okay, so when we subtract those, we get that the mass is different by this much. So I think that that mass is what becomes energy. In his last 1905 paper, Einstein finally said there's this deep unity between energy and mass, and he said that in fact energy is related to mass not just directly, but there's a conversion factor of c squared in there, which is the speed of light squared. So in other words, if you take how much mass you have, you multiply it by the speed of light squared, that's a huge conversion factor. You get a lot of energy. So this little guy might not seem like he produces a lot of energy in this transformation, this beta emission, but it probably is a lot. So what they did here is they just said, okay, take that, and they have basically a unit conversion. Can you see that? See, the U's cancel. So this much mass is equal to this much energy. So they're just doing it as a unit conversion. That seems kind of like a cop-out to me. What they're doing is going back to this page here and saying 1 atomic mass unit is this many kilograms, or it's this much energy. And that's crazy. It has mega electron volts divided by c squared. So for some of you, I know that's going to be hard to get a grasp on. You just need to think about it as going back to Einstein being able to say that energy is related to mass. So that much mass is this much energy. So it's 0.156 mega electron volts of energy. I don't really like that though. It's just a unit conversion. So let's talk about it another way too. And oh yeah, remember, when you do a beta emission, you get the daughter. That's the main biggest thing, right? You get also an electron, but you also get a neutrino. So let's draw that really quick, because we're gonna briefly read about neutrinos next. So we first got the carbon-14 guy, and when it decays, it kind of emits a variety of things. So you have like this little squiggly electron, right? That's the small guy. Then you also have maybe not so squiggly, but you get the daughter, which in this case was our nitrogen. And then you also have, we could probably think of it as, it's not really smaller, but you know, it's also a squiggly neutrino. So a neutrino. So also realize that there are neutrinos involved in beta decay. And that was a big thing for physicists back then. It was only recently that they actually definitely confirmed the existence of neutrinos. So hopefully we'll get to watch a video about that. Anyway, though, let's go back to my main point. I didn't really like this unit conversion here. It doesn't seem like they really did mc squared. I didn't see c in there anywhere, did you? So let's see if we get the same answer actually doing it directly. So in other words, energy equals the change in mass times c squared. So here's how it feels better to me. I said, okay, we figured out the change in mass was this guy up here, right? So I'm going to get rid of some of this junk. There we go. Okay, so the change in mass was this really seemingly small amount of about some 10,000th number of atomic mass units. So let's convert that, going back to here, directly into kilograms. You know, that's what I like doing in this class, is having masses in kilograms. Oops, I'm going to have to extend my page again. So what is it? It was 1.66, and I really encourage you to follow along in your calculator on this one. 0.5 times 10 to the negative 27th kilograms, so not very many kilograms, but kilograms nonetheless. And then, so that's the change in mass, and then we do c squared. So c isn't c3 times 10 to the 8th meters per second squared. So let's get that number. So I put that in my calculator, and I got, oh, it's getting sloppy. I really need a pad. I'll have to get one. So this is going to be equal to 2 points, and I'm going to round, but I'm going to keep it in my calculator, okay? So 107 times 10 to the negative 14th, and that's energy. This is all standard units. This is meters per second. This was kilograms, so that's joules. Okay, so we get joules, but if we go back up here, we say, hey, I don't see anything about joules. It's like an electron volt, so then we just do a unit conversion and say, okay, how do joules relate to electron volts? I think that if you go back and look somewhere in your book, or you just remember, we're going to have that there's 1.60 0.22 times 10 to the negative 19th joules in 1 electron volt. And the reason that makes sense is, remember, what is an electron volt? It's basically the amount of energy due to a single charge. It's the most fundamental charge. So if you have 13 electrons, that's 13 electron volts. So this is like basically the way you don't have to worry about remembering this is that this conversion between joules and electron volts is basically just the charge of an electron. So pretty easy there, yeah. Anyway, so then you divide those, so you get how many electron volts that is. So I did that with my calculator, and I got 156,701 electron volts. Can you see that right here? So if you write this, that's 10 to the 5th, so one more out here would be 10 to the 6th, or mega. So that's 0.156 times 10 to the 6th, or mega electron volts. Okay, so there's the direct computation. I hope you like that a little better. I certainly do. So what we're going to do is we're going to go do a little bit beyond the AP in terms of E equals mc squared and get some relativity stuff in there and do a couple examples on that next. So I hope you like that video. I think it's pretty neat. See you next time.